Hi viewers of Electronics Class Tanzania, welcome again to Lesson 9. In Lesson 8, we learned about voltage divider bias or self-bias. Also today, we'll continue with the voltage divider bias or self-bias. In Lesson 8, we have seen how beta of value of 150 beta, and we have seen the value of collector current. Also, we have seen the value of collector emitter voltage. Also today, we'll start with the beta of value of 150, and also we'll check again with the same parameters of the voltage divider bias or self-bias with the value of 100, and also we'll check again with the same values of voltage divider bias or self-bias with the value of 70 beta. In conclusion, you will see how the large changes of beta, but with minimum change of collector voltage and collector emitter voltage, which conclude that voltage divider bias or self-bias is more stable in such configuration. Today's lesson is lesson 9. Also, we continue with voltage divider bias or self bias. We'll see a circuit of a voltage divider bias. This is an NPN transistor. This is a RC collector resistor. This is our transistor here, NPN transistor. The arrow pointing outward is NPN transistor. Then we have our divider here. This is a RRE, our emitter resistor. And our circuit is grounded here. We ground our circuit here. So we have to name it. This is the RB1. This is RB2. Okay, let's put the values. This is the VCC, is 20 volts. RC is 10 kilo ohm. RE is 1.5 kilo ohm. And RB1 is 36 kilo ohm. And RB2 is 4 kilo ohm. This is our voltage divider because it divides here. Voltage divider bias circuit. This is NPN transistor silicon, which is VBE equals to, this is VBE equal to 0.7. We start with the beta of 150. RB1 is parallel to RB2. These are parallel. So let's have the Thevenin equivalent of this circuit. We'll put here Thevenin equivalent of this circuit. This is our source, Thevenin voltage. This is our Thevenin resistor. This is our NPN transistor here. This is our RE. We ground here. This is our RE. And this is our VCC. So we have collector here, we have our base here, we have our emitter here, and this is VBE voltage, and this is RB, Thevenin RB resistor. So we have to find RBB and the Thevenin voltage. Our RBB is equal to, this is a parallel, so RB1 times RB2 over RB1 plus RB2 equals to, RB1 is 36 times 4 RB2 over RB1 plus RB2, this 36 plus 4. We have here RBB, which is equal to, by calculator here, this is just a simple algebra. 36 times 4 is equal to 144 over 40, divided by 40 is equal to 3.6 kilo ohms. So we have to find also a voltage, Thevenin voltage, which is equal to VCC times RB2 over RB1 plus RB2 equals 220 times RB2 is 4 over 36 plus 4 is equal to 8 over 40, which voltage is equal to 2 volts. So here you have 2 volts, here we have 3.6 kilo ohms, and here is 1.5 kilo ohms, and here we have 10 kilo ohms RC. RC is here. So we have to find the IB. Can you use this space also? IB. IB is equal to V. IB. IB will flow this way. IB. V minus, which is here, 2, minus VBE over RBB plus 1 plus beta RE. Our V is 2, our VBE is silicon, this is a silicon transistor, our VBE is 0.7 over RBB is 3.6 plus 1 plus beta. The beta is 150, so it's 1 plus 150. RE is 1.5 times 10 to the power 3. This is a kilo, 1.5 kilo ohms. So we have here 1.3 over 3.6 plus 151 times 1.5 times 10 to the power 3. This is 1. So is another algebra, which you can have the values here, 1.3 over 151 times 1.5. So we have 151 times 1.5, and then it is 226.5 here. This value is 226.5. We plus 3.6. Uh, 151 times 1.5 is 226.5. 226.5 plus 3.6 is 230, 230.1 times 10 power 3. So we divide 1.3 divide by 230.1. We have here 0.0000564 milliampere, which also can be a microampere. We go forward 3.123, so we can have 5.64 microampere also. So this is IB. To have IC is equal to IB times beta. IB is this one, 0.00564 times beta, which is 150. So we have IC, we have our calculator again, 0.00564 times 150. We have 0.846 milliampere. This is our IC. And to have VCE, collector emitter voltage, is equal to VCC minus IC, RC minus IB plus IC in bracket RE. We have VCE. VCC is 20 minus IC is this one, 0.846 times RC is 10, 10 times 10 power 3 because it's kilo ohms, minus IB plus IC. So we have our IB here is this one, IB, this is our IB, and this is our IC. So I will sum up IB plus IC. I'll take this one plus this one. So it's another algebra, which is 0.00564 plus 0.846. We have 0.8516 times RE is 1.5 times 10 power 3. This is a milliampere. This is a milliampere. So we have here times 10 power 3 minus 3. That's a milliampere. And here, also this IC is also milliampere. This one, IC, is also milliampere. So we have here, can put here, we have here 10 power minus 3 also. So this one are cancelling each other. So we have here 20 minus, this have cancelled. We have 8.46 minus, so this are also cancelled. So it's 1.5 times 0.8. It's another algebra. I'll take a calculator. 0.8516 times 1.5 is equal to 1.2 0.2774. So our VCE equals to 20. We take 20 minus 8.46 minus 1.2774. We have 10.26 volts. This is our VCE. So I will keep my values because at the end we are going to compare when beta is 150 and when beta is 100 and when beta is 70. So I will keep my values, and the important values to keep is IC and the VCE. These values will compare them. So I will put them over here. So at beta, okay, I'll put them over here. I'll put them over here so that we can compare these values. Let's continue. We have our values here at beta at 150. We have IC. This is a milliampere. And we have VCE is 10.26 volts. This is our VCE. And this is our IC. So we'll do again with the same circuit and the values, but we change beta at 100. So beta at 100, our IB, because the RBB will be the same. RBB will be the same. Voltage will be the same. Changes will be on IB because the formula of IB is equal to V, which is this one, minus VBE over RBB plus 1 plus beta. This here we have the change, RE. Now the beta, we are changing the beta to be 100. So our IB automatically will change. So we have here 2 minus VBE because it is a silicon NPN transistor. So our VB is 0.7 volts. Over our RBB is 3.6 kilo ohm. This kilo ohms plus beta is 100. So 1 plus 100. Our RE is 1.5 K. This is kilo ohms. So we have IB is equal to 1.3 over 3.6 K plus 101 times 1.5 also K. This is kilo ohms. So at 10 times 3. So we have our algebra here also. 101 times 1.5. We have 101 times 1.5. Then we plus 3.6. Here we have 151.5 when we times this. 151.5. Then we plus 3.6. 151.5 plus 3.6 is equal 1.3 over 155.1, which is equal to 1.3 divided by 155.1. We have 0.00838. 0.00838. This is a milliampere. This is a milliampere. So you can also put in a micro. You move 3 decimal point to 8.38 micro. You can have macro ampere, but this one is a milliampere. So this is our IB. Our IB. Then our IC, the formula of IC is beta IB. So beta is 100 times IB. This one is 0.00838, which is equal to, we move 2 point, 0.83838. This is our milliampere. So this is our IC. Then we are looking for VCE, which is equal to VCE. VCE this one. VCE this one. This is VCE. Is collector emitter voltage. The formula is a Kirchhoff's voltage law, VCC minus ICRC minus, it's a summation here. We have summation of IB and IC with times RE, emitter resistor here. We have summation of IB and IC. Because IB is coming here, also IC is coming here. So here we have summation of IB plus IC times RE, which is this one, RE. So VCC is 20 minus our IC is this one. Our IC 0.838 times our RC is 10. This is K, kilo ohms, minus, and this is a milliampere. This is, so is 10 minus 3 here. IB plus IC. Our IC is this one, and our IB is this one. So, it's another algebra. I will take our IB is this one, 0.838 plus this one IC, which is 0.838, and our value here is 0.846. We times RE is 1.5 times 10 power 3. This is a milliampere, so we have here 10 power minus 3 is a milliampere. So this one cancel each other. Then we have a multiplication here. Also this one will cancel. We have 10 power 3 and 10 power minus 3. So here is 20 minus, then 0.838 times 10 is 8.38 minus, we take our calculator again, we have 0.84, we have 0.846 times 1.5, we have 1.269. So VCE, our VCE is equal to 20 minus this one. So we get, when we take 20, we minus 8.38. We minus again 1.269. We have our VCE as 10.35 volts. This is our VCE. So again, I will put this my values so that we'll compare. At beta, I'll put here, at beta 100, I get IC. My IC is 0.838. My IC is 0.838. Is this one, milliampere. And my VCE, my collector emitter voltage, is equal to 10.35 volts. Okay, then I will do some comparison. So I will clear my board again and we'll find the last beta at 70. Okay, let's continue now. Beta at 70. Yeah, beta at 70 also, there are values which will remain constant, like voltage will remain constant, Thevenin voltage will be constant, RBB, Thevenin resistor, base resistor will remain the same. But the change will be on IB and IC. So our IB, because the formula of IB is V minus VBE, is IB here, VBE over RBB, which is this one, plus 1 plus beta. So here the changes comes, times RE. There is a beta component here. So our V is 2 minus VBE is 0.7 over RBB is 3.6 plus beta now is 70. So 70 plus 1 is 71 times RE is 1.5. Of course, this times this K times 10 power 3. Of course, this one is also K. Here we have also times 10 power 3. This is kilo, 10 power 3. This is also the kilo ohm. So we have 1.3 over another, we take again our calculator, 71 times 1.5, 71 times 1.5 is equal 106.5 plus 3.6 plus, okay, let's put our value first here. 71 times 1.5 is, here we have 106.5 plus 3.6, 106, 106.5 plus 3.6. Yeah, we have 110.1. Of course, it is times 10 power 3 equals to 1.3. 1.3 we divide by 110.1. We have here 0.0118 milliampere. You can also use micro. We go right hand direction, 3 decimals. So 1, 2, 3, 1, 2, 3. So 11.8 microampere. So it can be also in microampere, but we'll always use that milliampere. So IC is equal to beta IB. So is equal to beta is 70 times our IB is this one. This is IB times 0.0118 equal to. So our beta is 70. We take 70 times 0.0118 So we have our 0.826 milliampere. So this is our IC. So we are looking again for VCE, collector emitter voltage. The formula is Kirchhoff's voltage law is VCC minus IC RC minus IC plus IB RE. This is our Kirchhoff's voltage law. At RE we have two current, IB coming here, also IC is coming here. So VCC is 20 minus IC RC. Our IC is this one, 0.826. This is a milliampere, so it's 10 power 3 minus 3 here. Our RC is 10 times 10 power 3 is kilo ohms minus, so we do with a summation is this IC plus IB. Our IC is our IC is equal to 0.826 plus our IB. Our IB, let's check our IB, is this one. This is our IB in a milliampere. So plus 0.0118. So we have 0.837, this summation, times 1.5, which is RE, which is 10 power 3, is kilo ohms. Here is 10 also, times is 10 also minus 3, because it's in a milliampere. So this one are cancelling each other. It's minus 3, positive 3. Also this are cancelling. So we'll have 1.5 times this 0.837. So 20 will be 20 minus, here's 10, so it's 8.26 minus another algebra. Then we'll take 0.837 times 1.5. We'll have 1 minus 255. So our VCE equals to, we take 20 minus 8.26 minus 1.255. We have 10.48 volts here. I'll confirm again. 20 minus 8.26 minus 1.255 is 10.48. So beta at 70. Beta at 70, we have IC. We have IC equals to 8.26 milliampere, and the VCE equals to 10.48 volts. Then I will remove this calculation so we can see the values clearly. So we can see the values clearly and see our comparison when we say a voltage divider bias or self bias is stable. The circuit stability is high, or the circuit stability is optimal because of its configuration. So I will put the values here. So in conclusion, let's put our values at different betas and see the comparison. The beta at Beta at 150, our values are here. I'm putting them here so you can see clearly. Beta at 150, beta at 150, our values IC equal to is this one, 0.846 milliampere, and the VCE, collector emitter voltage, is 10.26 volts, beta at 150. Beta at 100, beta is equal to 150. Beta at 100, our values are here. Our IC equal to 0.838 milliampere, and our VCE equal to 10.35 volts, and our beta at 70, our IC equal to beta at 70, our IC is 8.26 milliampere, and our VCE equal to collector emitter voltage is equal to 10 at 70 here is 10.48 volts. So, in conclusion, when we vary at large beta, we value beta at 150, beta at 100, and beta at 70. Big variation of beta. But take a look at collector current at beta at 150, this one, 0.846. At beta at 100 is collector current is 0.838. Very slight change. Very slight change. Also, collector emitter voltage is 10.26, and here is at beta at 100 is 10.35. Very small change. Also, beta at 70, we have this is 0.826 here. At 70. This is should be 0.826. Yeah. This is 0.826. So very slight changes. It is 0.826. Also, the collector emitter voltage at 70 also is 10.48. So also the changes are very slight. So in conclusion, we are saying the voltage divider bias or self bias is more stable configuration, because we have seen when we vary beta at large, we have very small change in collector current and collector emitter voltage. So self bias circuit is stable, is more stable when we vary beta. When we vary beta, because we have seen collector current and collector emitter voltage very slight change. This is our conclusion. At voltage divider bias, the circuit is much stable compared to the variation of beta. Hi viewers of Electronics Class Tanzania. In lesson 9, we have learned about voltage divider bias or self bias, and we have seen 3 scenarios: beta at 150, beta at 100, and beta at 70. but there were very small change in collector current and the collector emitter voltage. So we concluded that voltage divider bias or self-bias is much stable because we have varied the beta, but the collector current and collector emitter voltage changes very, very little. In lesson 10, also we are going to continue with transistors, and we'll see how we can manipulate and see how the transistor can do various work in our circuits. So don't forget to subscribe, comment and like and share so we can learn together electronics class Tanzania. Thank you so much.